In this lecture, I'm going to demonstrate how to perform naive-Bayes analysis in R. Naive-Bayes is a supervised learning technique that is designed to work with only categorical data for classification. In our example today, we will try to predict whether an individual is likely to earn an income that is below the poverty level based on his or her gender, race, marital status, age, and education attainment. In RStudio, I have imported the census data worksheet of the census data file into a data frame and named it My Data. If you have not done so, please import the dataset into R. Let's start a new script. To perform the naive-Bayes analysis in R, we need to use the following packages. If you have not installed these packages yet, please use the install.packages function to install them. After that, launch these packages using the library function. Since I have already installed these packages, I'm going to use the library function to launch these packages. You will need to use the correct package for data partitioning and performance evaluation. And you will use the club package for naive-Bayes analysis. And you will use the gains and the ROC packages for creating the graphic performance measures for the analysis. Let's run these 4 lines of code to launch the packages. Now let's first take a look at our dataset using the head function. So the result shows the first 6 records in our dataset. As you can see, the target variable poverty is of the double data type because currently there are numeric numbers in this field. We need to convert this variable into the factor data type as it is a classification problem, and we are going to do this using the as.factor function. And let's run it. Now let's use the structure function to take a look at the MyData data frame. And as you can see from the result, now the poverty field has been converted into a factor field with levels 0 and 1, indicating whether somebody earns a below poverty line wage. As we mentioned in our lecture, naive-Bayes uses a formula to compute the conditional probability of a case belonging to the target class. There is no need for optimizing model complexity. Therefore, the data only needs to be partitioned into training and validation datasets, using the training dataset to compute the conditional probability, and using the validation dataset to assess how accurately naive-Bayes can predict the class membership of future classes. Here, we will use the createDataPartition function to randomly partition the data into 60% training and 40% validation. In order for all of us to get the same random partitions, we will set the random seed to 1. Now let's run these 4 lines of code. In naiveBayes, since different target variable distribution resulted from the random case selection would impact the probability values used in computing the conditional probability of the future cases belonging to the target class. So in order to fine-tune the model to get the probability values that would lead to the most accurate prediction, R uses the k-fold cross-validation method on the training dataset to identify the best underlying distribution of the target variables and uses the option that yields the best accuracy. Now we are going to set up the k-fold cross-validation for the naiveBayes analysis. We specify the number of folds and the method of cross-validation using the train control function, and then we store the specifications in an object called myControl. The method option specifies that we are going to use the cross-validation technique, and the number option specifies that we are going to use the 10-fold cross-validation. Let's run this line. Before we perform the cross-validation, we need to ensure that we all get the same cross-validation results. So again, we use the setSeed function to fix the random seed to 1. We are going to use the train function to perform the naiveBayes analysis. We specify the model to use poverty as the target variable, and we are going to use the tilde and the dot to indicate that the rest of the variables are predictor variables. We are going to use the training dataset for the analysis and use the method equal to NB to indicate that we use the naiveBayes technique. And we are going to save the naiveBayes result into an object called nb_fit. Now let's run these 2 lines of code. And these 2 lines of code perform the naiveBayes analysis. In order to see the result of the naiveBayes analysis, let's take a look at the naiveBayes model by typing in the name nb_fit. nb_fit shows you the result of the naive-Bayes analysis. As you can see, through cross-validation, it was able to achieve an accuracy of 0.77 or 77%. Alternatively, if you do not want to use the cross-validation method, you can use the naive-Bayes function of the E1071 package. Install the E1071 package if you haven't done so. After installing the package, launch it using the library function, as I'm doing here. For the naive-Bayes function, in the package E1071, you need to specify the model, which uses poverty as the target variable and the rest of the variables as the predictor variables, and a specifier of the training data set for model building. We save the model in a new object called the nb_fit2. Now let's run it. Now let's take a look at the model by typing the name nb_fit2. And run it. As you can see from the result of this analysis, the model stores the probability values that are needed for computing the conditional probability of the new cases belonging to the target class. For example, it shows that the a priori probabilities are about 0.78 for y equal to 1 and 0.22 for y equal to 0. The conditional probability of married equal to yes, given the case belongs to the target class 1, is about 0.34, whereas the conditional probability of married equal to no, given the case belongs to the target class, is about 0.66, suggesting that married individuals are less likely to earn an income below the poverty line. As you can see, there are multiple ways to perform the naive-Bayes analysis in R. However, because the k-fold cross-validation method is less impacted by the way data are partitioned. So in this lecture, we are going to focus on the k-fold cross-validation method for performing naive-Bayes analysis. Now let's assess the performance of the naive-Bayes model created by the k-fold cross-validation method, using the data that was not involved in building the model, which is the validation data set. And we are going to use the predictor function to do that. And then we are going to use the confusion matrix function to create a confusion matrix. The predictor function specifies that we will apply the naive-Bayes model created using the tenfold cross-validation method to the validation dataset. The function will produce predicted class membership of the cases in the validation dataset using the default cutoff value of 0.5. The confusion matrix function requires two parameters. The first one is the predicted class membership, and the second one is the actual class membership in the validation dataset. The optional parameter positive specifies which class is the target or positive class. Since we are more interested in those who earn an income that is below the poverty level, we will use 1 as the positive class. Now let's run these two lines of code. Now let's take a look at the confusion matrix that was produced. As the confusion matrix shows, the model has an overall accuracy of about 0.76, sensitivity of 0.77, and specificity of 0.72. This suggests that overall 76% of the validation cases are correctly classified, and among the target class cases, 77% are correctly classified, and among the non-target classes, 72% are correctly classified. Overall, the model has moderate predictive performance. If we compare the model's performance measures with those of the naive rule, where all cases are classified into the predominant class, the model's predictive performance is not very impressive. This dataset happens to oversample people making an income that is below the poverty line, which means that an overly large portion of the cases in the dataset are target class cases, and the distribution of the target and non-target class may not represent what is in reality. Among the 9,980 cases, there are 7,788 target class cases, and that accounts for 78% of the cases. So using the naive rule, if we classify all cases to the predominant class, which is the positive class, we would have an accuracy rate of 78%, sensitivity of 1, and a specificity of 0. So as you can see, even the naive rule would have a slightly better accuracy rate than our model. However, the downside of using the naive rule is that it does not differentiate people who make below or above poverty incomes, so it is really useless. Our model, at least, is able to help us identify most of the people in both classes correctly, so it is more useful than the naive rule, even though the confusion matrix measures would tell you otherwise. This just shows that using only one performance measure to assess a model's performance is often biased. You should incorporate multiple performance measures as well as the properties of the dataset and the business context to get a more comprehensive understanding of the model's performance. We have also discussed that sometimes the default cutoff rate of 0.5 is not necessarily the best cutoff value for the situation. The analyst may choose to increase or decrease the cutoff value to classify fewer or more observations into the target class due to asymmetric misclassification costs or uneven class distributions. In this example, we have uneven class distribution. 78% of the cases belong to the target class, suggesting that the probability of an individual making below poverty income is 0.78 instead of the default probability of 0.5 for a binary choice situation with equal class distribution. Therefore, in this case, it may make sense to increase the cutoff rate so that you don't overclassify people into the target class, meaning classifying too many individuals who make over poverty line income as people who make below poverty line income. Let's see what happens if we increase the cutoff rate to 0.75. To do this, we first need to compute the predicted probability of each case belonging to the target class by setting the option of type to prob in the predict function. And we are going to save all the predicted probabilities in an object called nb_class_prob. Let's run this line of code, and then let's take a look at some of the probability values. As you can see, the result shows the probabilities associated with the first few cases. The first column lists the probabilities of the cases belonging to class 0, which is not below poverty line, while the second column lists the probabilities of the cases belonging to class 1, which is below poverty line. So to determine the class memberships of cases using a cutoff value of 0.75, we compare the values in the second column to the cutoff value of 0.75. To construct a confusion matrix, we are going to use the if-else function to determine the class memberships. And we will use the as.factor function to convert the class membership to factor, which is the same data type as the target variable poverty. Now let's run this line of code, and we get a new confusion matrix. As you can see from the result, when we increase the cutoff value to 0.75, the model's overall accuracy and sensitivity decreased to 0.74 and 0.71 respectively, but the specificity increased to 0.83. So with the cutoff value of 0.75, we are getting better at classifying individuals who make above poverty incomes. Now let's create the graphic performance measures, including the cumulative lift chart, decile-wise lift chart, and ROC curve. These performance measures are important because they are not affected by the choice of cutoff value as the confusion matrix does. Both the cumulative lift chart and the decile-wise lift chart are constructed from the gains table that can be created using the gains function in R. The gains function requires that we convert the target variable to numeric ones and zeros. So we are going to first convert the target variable poverty to character and then to numeric. Let's run this line of code. And then we are going to create the gains table using the gains function. As you can see, the gains table requires two parameters. The first one is the target variable property of the validation dataset, and the second parameter is the predicted probability of the validation cases belonging to the target class. And let's take a look at the gains table by typing in the name gains table. We have discussed the components of the gains table when we demonstrated how to perform k-nearest neighbors analysis in R. So I'm not going to repeat this here. If you are not clear about what the gains table means, please refer to the recorded lecture on performing KNN in R to refresh your memory on this topic. But here's the gist of it. The gains table shows 10 groups based on their probabilities of belonging to the target class. The first group, which consists of 490 validation cases, accounting for 12% of all validation cases. All these cases are target class cases because the mean response is 1.0 or 100%. And these account for 15.7% of all target class cases in the validation dataset. The lift for these cases is 128% or 1.28, suggesting that if we take the 12% of the validation cases with the highest predicted probability of belonging to the target class, we will be able to identify 1.28 times as many target class cases as if we just randomly select 12% of the validation cases. This shows the improvement of our model over random selection. The last column shows the average predicted probability of the cases in this group belonging to the target class. In this case, all these cases have a predicted probability of 1 of belonging to the target class, hence the average of 1. But keep in mind that this number is rounded to 2 decimal places, so the actual predicted probability may not be exactly 1. It may be 0.999. So to confirm that, we can use this command. As you can see, we are sorting the predicted probability of the validation cases belonging to the target class in descending order here. Let's run this line of code. Here we have a sorted list of the probabilities. If you scroll to the top of the list, the first few hundred cases all have predicted probabilities of belonging to the target class of 0.99 or higher, which usually round up to 1. That confirms what we saw in the gains table. So now let's create a cumulative lift chart. We are going to use the plot function to do that. Let's run this line of code. And we can see the cumulative lift chart appearing on the right side of the screen. So as you can see, the plot command plots a line chart with two sets of coordinates. The first set, plotted along the y-axis, is the total number of target class cases. And the other set, plotted along the x-axis, is the number of observations. So the cumulative lift curve shows the depth of the number of cases versus the number of target class cases identified. When the lift chart arches above the diagonal line, as in this case, it shows that the model is able to identify a larger percentage of the target class cases by only looking at a small percentage of cases with the highest predicted probability of belonging to the target class. And this shows that the model performs better than random guess in classification. So we can use the lines function to draw the diagonal line that represents the performance of a random guess. To show the diagonal line, let's type in this line of command. We are going to show the diagonal line using the color red and also using dashed line. Let's run it. As you can see, now we see a red dashed line, which is the diagonal line that represents the random guess. A lift curve that arches above the diagonal line indicates a better than random selection predicted performance. So in our case, our naive-Bayes model performs better than the random guess. To create the decile-wise lift chart, we use the bar plot function to create a bar chart. The bar plot function requires one parameter, which is the height of the bars. In this case, the height of the bars are represented by the lift values for the groups in the gains table. More details about the decile-wise lift chart can also be found in the recorded lecture on how to perform k-nearest neighbors analysis in R. Please review it if you need to. The decile-wise lift chart presents the same information that is in the cumulative lift chart, but in the bar plot format, which is usually quite telling about how much improvement the model has over a random guess. Let's run this line and see the decile-wise lift chart. As you can see in this case, the chart shows moderate improvement over the random guess with higher than 1 lift for the first few bars, and the lift values start to taper off in the later bars. One thing to point out is that during our lecture, we mentioned that since naiveBayes makes the variable independence assumption in its formula, so the computed probabilities may not always be very accurate. However, the ranking of the probabilities is usually more reliable. Both cumulative lift chart and decile-wise lift chart show the probabilities ranked from the highest to the lowest for all the validation cases, so they are very useful in assessing model performance in naiveBayes. Probably more important than the performance measures from the confusion matrix, which only looks at the predicted probability values in the case of naiveBayes. Finally, let's construct an ROC curve. The receiver operating characteristic curve shows the sensitivity and specificity across all possible cutoff values. We are going to use the ROC function, which produces an ROC object that can be used to plot the ROC curve. We then use the plot.roc function to plot the ROC curve and the AUC function to retrieve the AUC value. Let's run the first 2 lines of code first. By running the first 2 lines of code, R is going to plot the ROC curve for us. The ROC curve shows that the naiveBayes model performs better than the baseline model, which is shown as the gray diagonal line in terms of sensitivity and specificity across all possible cutoff values. And then let's run the line for the AUC value. As you can see from the result, the area under the curve, or AUC value, is relatively high at 0.8437, indicating that the naiveBayes model performs relatively well. One thing to keep in mind is that the AUC value ranges from 0 to 1, 1 being the model is perfect, and the baseline model, shown as the gray diagonal line, should have an AUC value of 0.5. So in our model, the AUC value is closer to the perfect model than to the baseline model, suggesting relatively good performance in terms of sensitivity and specificity across all possible cutoff values. Now let's take a look at how we can score new cases with our naiveBayes model. To score the records of the score dataset, I have imported the data from the census score worksheet of the census data file into a data frame and labeled it My Score Data. And as you can see in the score data, I only have the predictor variables. Now we are going to apply the naive-Bayes model to the score data set. We are going to save all the predicted membership in a new object called nb_class_score. And we are going to use the predict function to apply the naive-Bayes model to the score data. Let's run it. The result of the predict function are class memberships using the default cutoff value of 0.5, and you can always use a different cutoff value to classify, as I showed you earlier. We will put the class membership along with the original score data. And then take a look at the score data with the class membership using the view function. Now let's run these two lines of code. The view function is going to open the MyScore dataset and show it in the spreadsheet format. Now let's take a look at a few records here. According to our naive-Bayes model, the first individual, who is an unmarried white female without a college degree, is likely to earn below poverty wage. And the very last record of a married white male with college education is not likely to earn below poverty wage. So this is how to perform naive-Bayes analysis in R. Since naive-Bayes can only be used for classification, you should not use this technique for prediction problems. Also, all predictor variables need to be categorical. In cases where some of the predictor variables are numeric or of the date data type, you can convert them into the categorical data type using the binning technique discussed in our data wrangling lecture.